The problem I'm going to do, I'm calling minimum time of descent for a block on an incline. So we have an incline here. The incline has an angle of alpha with respect to the horizontal. The base of the incline is 1.5 meter, and the coefficient of friction on the block is 0.4. So we have a choice of what we can make the angle. We could reduce the angle of the incline, but we still have to keep the horizontal distance 1.5, right? So 1.5 meters, and then if we reduce the angle of the incline, what's going to happen? Okay, so if we reduce the angle of the incline, one of the things, the distance that it's going to travel is going to be less. So you would think that if you reduce the angle of the incline, it's going to travel less of a distance, right? So it should get there quicker. So the idea is I want to find the most minimum time. What angle achieves the most minimum time? So you would think, oh, okay, just keep the base the same, just have the angle less and less, and you would get there quicker because it has less distance to travel. But hold on to your seat here. There's a couple competing factors going on, right? You have the normal force, then you have the mg, right? And then you have here mg cosine theta, then you have here mg sine theta, right? Or we can call it alpha, mg sine alpha, mg cosine alpha, right? So if I make the angle large, what's going to happen? The mg sine alpha is going to go larger, right? The mg cosine alpha is going to get smaller. Okay, that's good. We want that to happen. We want the downward component of the weight to get larger, and we want this component of the weight to get smaller, because if this component gets smaller and smaller, the normal force gets smaller, and the friction force on the block gets smaller, right? So the forces on the block are like this. We have a normal force, we have here mg, we have here mg cosine of alpha, we have here mg sine of alpha, then we have here the friction force mu kn. So with that argument, it would make sense that you want the angle to be large, right? Because if it's large, this component gets larger, this component gets smaller, and the friction gets smaller. And if there's less friction and there's more downward component of the weight pushing the block down, the block should get there quicker. But you don't want the angle to be too large, because then the distance will get too large, right? So there's a competing factor going on here. mg sine alpha minus mu kn is equal to ma. Then we can substitute the fact that n is equal to mg cos alpha. mg sine alpha minus mu k mg cos alpha. And then the m and the m cancel. So the acceleration is equal to g sine alpha. We can factor out the g. G sine alpha minus mu k cosine alpha. Okay? So you can see how the acceleration depends on alpha. If we make the alpha larger, what's going to happen? When we make the alpha larger, sine of alpha will get larger. And then when we make alpha larger, cosine of alpha will get smaller. So if this number is large and this number is small, that's good, because the acceleration of the block increases. But then hold on, the distance gets longer, right, when you make the angle larger. So what's this distance? We can say cosine of alpha is equal to 1.5 meters divided by the distance that it has to travel, right? So if we make the angle large, the distance gets large, okay? So how do we calculate the time that it takes for the block to go from here to here? What's the general equation? Okay? We can use one of the equations of kinematics, right? Which one should we use? We can say x final is equal to x initial plus v initial t plus half at squared, right? And then x final is going to be basically the final distance, and then x initial is 0, right? So x final is actually this distance, the distance that it has to travel to go to the bottom, right? So this is d. V initial is 0. Then we have here half at squared, right? So the time that it takes, the t squared is equal to 2d over a, okay? So the equation for the time is like that, 2d over a, and then my d is going to be what? D is going to be 1.5 over cosine alpha. So then I could put that there. 2 times 1.5 over cosine alpha. Right? So that one is for the D, right? And then the A, so I just put the reciprocal of the A, right? So then I just put here G. Then I put here sine of alpha minus mu k cosine alpha. Okay? So then what's the general equation for t squared? Okay, so we have here t squared is equal to 2 times 1.5, that's 3, divided by g is just 9.8. Okay? And then I can distribute the cosine of alpha. Cosine of alpha goes into with the sine of alpha. It makes that what? Cosine alpha, sine alpha, which is sine of 2 alpha over 2, right? Sine of 2 alpha over 2, right? And then cosine of alpha goes into here and makes it cosine squared alpha minus mu k cosine squared alpha. Okay? So that's equal to the t squared. So what am I going to solve for? If I want to minimize the t function, if I want the most minimum t, what do I want? I want to find the angle that maximizes this expression, right? I want to maximize the denominator, because if I maximize this function, I can minimize the time, right? So then I can take this here. I can define the function f of theta, or f of alpha, is equal to sine of 2 alpha over 2 minus mu k cosine squared alpha, right? And then I want to find the angle that maximizes that. So then I take the derivative of that. Then I get here cosine of 2 alpha times the derivative of the inside, which is 2. And then that cancels this 2. Minus, and then the derivative of this becomes 2 mu k cosine alpha, right? Times the derivative of cosine, which is negative sine, right? Negative sine alpha. Then I'm going to set that equal to 0. Okay, so then what's that going to be? I have here tangent of 2 alpha is negative 1 over mu k. Okay, so then we can put whatever value of mu k is. So if I want to maximize this function, I use this alpha given by this condition. Then once I find that angle, I can put it into here and I can actually solve for the most minimum time, right? So let's say our mu k was 0.4. So then this would be negative 1 over 0.4, right? So there would be 1 divided by 0.4, that's negative 2.5. Negative 2.5. Then I would take the tangent inverse of that, and I would get 1985, right? But what you have to do is, the other angle where the tangent is negative is add pi to it, right? So this is something we're forced to remember, something we learn in trig, right? So what it's telling us is tangent of 2 alpha is negative 2.5, and we know that the tangent is negative in the 4th quadrant, and it's also negative in the 2nd quadrant, right? So then the negative 68.5 is the answer in the 4th quadrant, right? Negative 68.5, 0.1985. So if I add 180 to that, if I add 180 to this, what do I get? Plus 180, I get 111.8. So then I get 111.80 degrees. So then 2 alpha needs to equal 111.8 degrees. So then what's alpha need to equal? Right? So then alpha is going to equal 111.80 divided by 2. And then that's going to be 55.9 degrees. So if I want to make the shortest possible time, depending on the coefficient of friction that was given, I need to make my angle 55. If I make it larger than that, yes, I am increasing the acceleration, but I'm increasing the distance too much. And then the distance of travel will become too large, and that will make the time large. So then let me take that angle, and then let me put it into here, and then that will tell us what the time is. So I'll put here 0.4 seconds. Okay? So remember, my base, I haven't changed. My base was still 1.5 meters. Now, what if the friction coefficient was 0.2? What should now the angle be, right? So then I'll have here 0.2. Okay. So then 1 divided by 0.2 is going to be negative 5. So now it's going to be negative 5 here. Right? And then when I take the tangent inverse of that, it's going to give me negative 78.69. Negative 78.69. So what happens when the friction coefficient gets smaller, the tangent inverse gets more of a negative, then I'm going to add 180 to that. I'm going to add 180 to that, and then that's going to give me 101.3. So what happens, this number gets bigger in the negative direction. Then when you add 180, now it's a smaller positive number. Then I divide that by 2. And then now I get alpha should be 50.65. So if it's a smoother surface, what you want is you want to reduce the angle. Why? Because the only reason we're increasing the angle is for surfaces that are more rough, in order to decrease the normal force. You get the idea? So surfaces that are rough, when mu k is large, we're increasing this. We're sacrificing the distance, but we're increasing the angle in order to reduce the normal force. But if the coefficient of friction is smaller, it's only 0.2, then I only need an angle of 50, right? So that my angle doesn't need to be as large. You get the logic of that? So it completely makes sense. Okay? So then what's going to happen, it should now take much shorter than this, because the distance it has to go is less, and also the friction is less, right? Because the angle is less, the distance is also less, right? So, so then it should be here. We put the angle here. Let's see here. Cosine of alpha. So it makes sense, you see. The angle required is less when the friction is less, and the time that it takes to get there is also less, because the friction is less and the distance that it travels is less, right? So it gets there in a shorter time and the angle required is less. So you can see a good example where we did some free body diagrams, and we used some calculus in there, and we used some trig. The fact that the tangent inverse function gives you negative, but then we added 180 to get to the right quadrant, right, in order to solve it. So many tools are needed to be able to solve something like this correctly, and then to analyze the meaning of it and see that it makes sense, okay? Thank you very much.